Our next speaker is Adilson Motter from Northwestern.
All right, thank you very much. Can you all hear me in the back of the room?
No.
I will be a little bit more specific than Dan. I knew that he would give the first talk, so I will skip a lot of my introduction.
Could you raise the
And I will go straight to my main points. So one of the things that I want to talk about is the opportunity that many of the transformations that are about to happen with power grid give us in terms of solving a very old problem with the grid, which is the existence of large-scale failures. This is work that I've been doing with a number of collaborators, especially students and postdocs in my group, well funded by those agencies. We are an energy-intensive society. Even though the United States is no longer the main producer of electricity in the world, since 2011, China took that place. It's still one of the main producers, it's now the second largest. The consumption of electricity per capita in the US is about 1,400 watts. And given that electricity is about 40% of the commercial energy that we consume, this accounts for about 35 to 40 times the amount of metabolic energy that we consume. Each of us, an adult, consumes about 2,000 calories a day. That's about an incandescent lamp. So this is perhaps one of the most significant changes between primitive man and modern man, the amount of energy that we consume in addition to the immediate biological needs that we have. An important thing is that it's only 40% now, and that number is likely to increase because transportation responds for 30% of the commercial energy. And with the transition to electrical vehicles, we would expect that good part of that would be transferred to electricity, even though, of course, efficiency may come into play and cut this down. Now, when you look at the projection for new installed power in the US, in 2018, we already had more than 50% coming from renewables, and that trend is going to continue. Here's what we have for the year of 2019. You see there will be mostly renewable and natural gas, replacing things like coal. So this is an opportunity because it's the first time since the Second World War in which the grid that has been upgraded in very slow pace will be redesigned to a large extent, and that gives the opportunity to optimize certain things that are far from optimal now. It might come as a surprise that a system that has been designed and engineered in all aspects and operates well under normal conditions sometimes undergo failures like this one. And this is far from being the largest one in the world. I think India still holds the record. And pretty much everywhere in the world, we have seen large blackouts. One of the few exceptions is China over the last 10 years, precisely because they have the benefit of having an infrastructure that's much newer than ours. In addition to that, of course, they do not have trades of energy in the same way we have here. So policy is also a factor there. But the question that I want to discuss is, given the costs of these failures, what can we do to minimize them? I guess the first question is what causes them. They are usually caused by small, localized failures that amplify as they propagate in the form of cascades. And that leads to a number of questions. What are cascades, how they propagate, how to predict what would be the sizes of cascades given certain conditions, and what we could do to mitigate them. The problem is that the main events here, the large cascades, are rare events. So we cannot rely on historical data only to make predictions. And that brings to my main point, that is, one of the important neglected technologies that's needed here is the development of reliable, realistic models to simulate the various scenarios that are relevant for the grid, so that we can get ourselves away from just n-1 contingent tests. And that's what I will be talking about for the rest of my presentation. So a cascade, just to make a point here, is different from most other spreading processes in networks. And it's different in the following way. It's a complex contagious process. The failure of a component in the network depends on multiple exposures to failures. It's completely different, for example, from the spread of flu. The likelihood of me getting the flu from Richard, if he has the flu, would be completely independent from my previous exposures to others from whom I failed to get the flu. In the case of cascades, it counts. It's cumulative. And that changes a lot the type of models, the type of mathematical models that we can develop to predict the outcomes of events like this. And in a sense, it is a domino effect, but it's a particular type of domino, more like this one, in which you have built-in amplification as it spreads. If your question is just to predict the size of cascades, some early work that we developed in this area can give you reliable predictions, at least statistical predictions, without knowing the details of the dynamics, by only using two statistical ingredients. One is obvious, is the vulnerability of the individual components, the likelihood that they would fail. The second is what we call co-susceptibility, is the likelihood that two or more elements would fail together. Now, when you put together those two elements, no matter what dynamics gave rise to them, you can make predictions about cascade size that really are close to what you'd have from direct simulations. So here's an example for Texas. On the left side, you see the correlations between cascading events. This is in the absence of any correlations in triggering events. So it's really due to the structure of the network and the dynamics, which is highly structured. Now, in addition to that, you have to account for the fact that most of the failures in the network are initiated by weather events and are therefore necessarily correlated. They tend to be co-localized and they tend to co-occur in time. So this is a lower bound for co-occurrence, if you like. The right side is just a verification that within 9.5 confidence interval, the predictions match the actual cascade size. Now, if we want to go beyond that, if we want to make predictions about the identity of the elements involved, then we need a much more elaborated model. And this is something we have been working for years on to build such a model that would give us the ability to make predictions that account for the continental scale of some of these events. And for that to be possible, we have to have a model that includes all the parts that are connected. In this case, all the three main interconnections of the United States, which also include the southern part of Canada, which is where most of the Canadian population is. So the physics has to be included, but also the operational practices of how operators would likely respond, and relays and automated systems would respond to failures. And the main and most important thing that is left out of most of the previous literature on trying to understand cascades is to account for the fact that over a year, we go through many different conditions of power demand, power generation, and And this is going to be even more pronounced as we increase the share from intermittent sources. At the end, we want to have something that looks like this. You have a model of the grid. In our case, this model includes about 100,000 power lines in the United States and South Canada. And you want to disturb this network, in this case here, by perturbing 3 power lines, and see what happens. And as you evolve the dynamics of the system, it might grow into a cascade like the one we have here. And you can already learn a lot of things from this very example I'm giving you, which was generated with the model we built. In this case, you can see that the cascade propagates in a non-localized way. You can see that failures are not connected with each other. You can have failures jumping around, but it's also somewhat contained. This is just the southern part of Canada, including part of Florida. So the map that I'm showing you is the box of the entire map of the United States, South Canada. This map looks funky because we dense equalized it. Let me mention something else first. In this representation, green represent the power lines that do not fail, and gray the ones that fail. I want you to see that there is a lot more green than gray, even when we simulate hundreds of thousands of scenarios here, and of events. And we considered many different conditions, in this case, 15 between the years of 2008, 2013. The grid increased by about 2% a year in power generation of this period. So there's a non-negligible change in the grid over this period. And yet, at the end, you have about only 10% of the power lines ever failing. So this is really a story of robustness, if you wish. Now, why did we stop in 2013? Because that's when we started building this model. It took 5 years for us to complete the design and, most importantly, the validation against historical data. When we published it in 2017, that was the data set we were working with. But now we can upgrade it easily, and I'll show you at least a couple of figures for 2018. Let me just show you what's going on there. So this is a short story of what we did. Our starting point is data from FERC, which is only one of the pieces here. And that allows us to identify the power stations, the transmission lines. And one of the things that we want to do is to eliminate heterogeneity due to the heterogeneous way in which population is distributed in the US. That is reflected in the way in the way energy is consumed. And that's what leads to that graph that we were showing. That also solves a problem of not having to show sensitive information, because it's very difficult to reconstruct the network from this figure that I'm showing you now. And it's on top of this that we can run all sorts of scenarios and do statistics about cascading failures. Those are examples of cascades. And you see that we are keeping in yellow the vulnerable lines. Those are lines that physically fail, either because they are damaged or because they have to be turned off. There are other lines that undergo outage because they are de-electrified due to the failure of the primary failures. Now, the top is the portion that fails. As I said, just some 10%, even in the worst case scenarios we are considering here. And the bottom is the part that is not failing at all. So when you look at something like this, you can start asking questions then about what's happening and what we can learn on top of what I have already shown you. Here is a different representation in which each pixel is color-coded by including essentially showing the likelihood that lines connected to that area would fail. And when you look at this, you see that's more or less evenly distributed across the country once we dense equalize the power stations. But this is what we see when we are victims of a power outage as customers. But you have to, again, separate what is an actual failure, a primary failure, from the consequence of that, the other lines that will be turned off because they are downstream from there. And the primary failures are very heterogeneously distributed. You have big areas in which none of them would ever fail, and other areas in which they are concentrated, even after we control for the heterogeneity of the grid. Here are the secondary failures, here are the primary ones, and here are all of them. Now, this is important because the primary failures are really the ones we should be focusing on. And then you can try to understand more by looking at the structure of the network. This is what network scientists would have started with from the beginning. In this case, it turns out that a good measure is is something known as corners. Is a measure of how many connections a component has with the rest of the grid as you trim it. For example, the nodes that are connected to one power line, when you remove them, you are left with another one that's connected to just one power line here. So that 2 is counted as having just one connection. And we say that's a node of corners 1. Then you are left with nodes that only have 2 connections, that have at least 2 connections with the rest of the network. So they are at least corners 2 and so on, up to the point where we are left with no node at all. When you analyze the network from this perspective, you see that you have many more elements of low corners. But when you normalize by the number of elements of each corners, you see that the failures are more likely to happen with high corners elements, precisely the ones that are central to the network, which again are the ones that have more impact on others once they fail. So the primary failures, which are...
We're recording, and so we need to have it through the microphone.
I'm very stimulated by this, but I'm trying to grasp sort of individual elements of it. So I'm going to ask you a question at sort of the, not because I demean this, but because I'm trying to connect it to everyday life or something. Where I would try to phrase a sort of practical example. What, can you do things like in this, analyze the difference in the likelihood of small cascades that lead to big cascades between a neighborhood which is got the power lines in the ground as opposed to power lines in the air, for instance?
No, that's an excellent question.
My sort of casual observation is people tend to not want to pay money for future difficulties at all scales. So, but the people that have underground lines, unless there was some initial choice of bad materials and so on, which does happen, but assuming that's not happening, you pay more at the beginning, but I think the proof is that over a longer time, that individual net doesn't suffer from ice storms, from electric storms, from tornadoes, whatever. But can you build that kind of looking at an element into this? And is there any evidence that these places that tend to go have something to do with something like I'm using as a concrete example?
No, that's a good question. We have a project now that's trying to account for weather conditions across the United States and extreme weather, which is not quite what you are asking about, but touches on some of those issues. The images I showed you here were intentionally generated with the assumption of uniform likelihood for triggers. So we are treating every part of the grid as a potential trigger for a cascade. In practice, that's not the case. In practice, you have a lot more failures associated with extreme weather in some areas of the country. For example, in the East Coast, there is a lot of interest in trying to understand the impact of hurricanes and summer storms, because when you look at the data, even though there are areas in which it's unavoidable to have an outage because the storm is so severe, there are other areas that are also undergoing outage that could, in principle, have been saved from that outage. So there is a lot of space for improvement there. And your question about the physical part of the grid, yes, there is a lot can be said about that. Also, a lot can be said about the type of power generator that is involved. Okay, some forms of generation are more robust to weather conditions than others. And all of that can be accounted for in a realistic way, if you wish. But I think we are not quite there yet. There are more fundamental questions to ask that relate to the question of being able to really reproduce the dynamics of the system reliably, so that the cascades that we are observing in simulations are similar to the ones that would happen in reality.
I mean, Norway would be an interesting example. Sorry. Just Norway, that's undergrounding quite a bit right now. They already have a reliable system. Would be an interesting comparison to yours because they have, I mean, they have the money to do it, and so they're taking this up.
And they are also interesting because of the way in which they produce energy, which is mostly renewable.
I wrote in '81 for the Pentagon what's still, I think, the definitive unclassified work on grid vulnerability and resilience, but it was completely qualitative. We didn't have any of the wonderful tools you've shown us. And it makes me wonder what your analysis might show about the resilience value, if any, of much more decentralized or granular resources that are organized fractally so that you can have microgrids that can normally interchange but can stand alone in need. Can those damp the propagation of cascades?
Yeah, that's, I have my microphone thing. It's an opportunity, of course, because the dilemma with networks and power grids in particular is that the same connectivity that gives rise to functionality is also serving as a conduit to propagate failures. So microgrids eliminate that problem because they can, by and large, operate in the disconnected mode. So you would have the opportunity with proper sensing to disconnect when needed. I do not think, however, that the near future will be as heavily based on microgrid as some project. What I'm seeing happening in the industry is that most of the main players have one microgrid where they do research, but they are investing their assets on other forms of generation. Renewable, yes, but I don't see the network 20 years from now being formed primarily by microgrids, at least not in the United States.
Okay, we have time for one more question. Else we'll move on to our next speaker. All right, let's thank Adilson.